Okay, so we're trying to answer the question, how special are conformal field theories? And we're going to start off by answering a simpler question. Let's just ask what quantum field theories, so let's ask what quantum field theories are invariant under a scale, under scale transformation. Okay, so what I have in mind is something pretty simple. We're just going to take x mu and we're going to scale it into lambda x mu. And we want to know which quantum field theories would be invariant under that. And remember, as usual, we'll be using units in which h bar is equal to c is equal to 1. So the only unit that I'll have left, the unit that I'll use, is the unit of length. Okay? So after setting h bar is equal to c is equal to 1, I must pick what units I'm going to have. I'm always going to work with length. So let's start off. Let's imagine I had this equation. So d mu phi, and let's say plus m squared phi is equal to 0. So this is a free massive scalar. Okay, let's see if this has got a hope of being conformally invariant. Well, the first thing that you notice is under this scale transformation, we know that these derivatives, d mu will transform. Phi might transform, so we might have to say how it's going to transform, but those two terms will transform in exactly the same way because phi will be transforming. But this term will not transform, and it won't transform because m squared is some parameter that you've given me. It's some mass squared. And of course, if I just change coordinates, x mu into x tilde mu equal to lambda x mu, why on earth would the mass change? It won't change at all. So in fact, the free massless scalar has got no hope of being invariant under this coordinate transformation. And one way of seeing that is that an intuitive way of seeing that is that this mass squared sets a scale, or it sets a unit for me. I might say that 1 unit is 8m squared, something like that. So if you tell me that something is 10, well, I know it's actually 80m squared. And if I choose to change my scales, here change my length, you know, things will not look the same at different scales. Something which weighs 1 is definitely different to something which weighs 10. And of course, changing length is the same as changing mass because here length is the only unit I've got, so mass would be an inverse length. And this is a pretty general conclusion, in fact. Um, your theory, so let's say your theory can only be scale invariant if it doesn't have a specific scale. So that means if it has no dimension full parameters. As soon as you have a parameter which has dimension, you have set a scale. Okay? So you better have a theory that has no dimension full parameters. Okay, so with this insight, let's make another guess. Well, a better guess could be to take d mu phi is equal to 0. So in other words, a free massless scalar. And in fact, it turns out that that is a CFT. There is a CFT based on the free massless scalar. This theory has no dimension full parameters. Another example would be to take d mu, f mu nu is equal to 0. And here by f mu nu, I mean the electromagnetic field strength. So d mu a mu minus d nu a mu. So what is this? This is a free photon. I can give you another example. If we take gamma mu, this is Dirac's gamma matrix, on gamma mu onto some fermion field psi, So this would be a free massless fermion. This is also an example of a conformal field theory. So these three theories, actually, even at quantum level, it turns out that they are scale invariant. They're full conformal invariant. But this is pretty disappointing because if the only examples of CFTs that there are free theories, well, we don't think that we're going to learn very much from this. So now let me give you an example of a theory which does look scale invariant, at least at the classical level. So let's specify this Lagrangian density. So the Lagrangian density is 1/2. We've got d mu phi, so the usual kinetic term. Then we've got minus g phi to the 4. Okay, so let's try to figure out why this would be at least classically scale invariant. Now remember, the action has the same dimensions as h bar, and we're using units in which we've set h bar to 1. So length to the naught. H bar is length to the naught. So if we want the action to be length to the naught, remember that the action is equal to the integral d4x of the Lagrangian. So I'm working in 4 dimensions. And we know that d4x is length to the 4. It's a little volume. This is a space-time volume. It's a length to the 4. Remember, time has the units of length if we've said c is equal to 1. And that means that the only way that the action can come out as length to the naught is if the Lagrangian density itself really is length to the minus 4. Okay? So this must be length to the minus 4. Now, look at this term over here. And of course, you know that d mu is length to the minus 1. So we've got two derivatives that'll give us length to the minus 2 and 2 phi's. So the way that that first term becomes length to the minus 4 is if phi itself is length to the minus 1. Good. Now, if phi to the 4 is length to the minus 1, you see that in the second term over here, if phi itself is linked to the minus 1, in the second term you see that phi to the 4 itself is already linked to the minus 4. And that means that the coupling must be linked to the naught. So that classically, this theory has no dimensionful parameters. So this theory has no dimensionful parameters. And that means, well, at least classically, so let's say classically, it is a scale invariant. Okay, so the theory has no dimensionful parameters, so classically, it is indeed scale invariant. Good. Okay, so great. So we seem to have an example that at least classically is scale invariant. Now, how generic are these, or how carefully did we have to tune things? Well, I'm going to give you a little exercise now. Okay, so here's an exercise. So what do I want you to do? Take this as your Lagrangian density. So keep the kinetic term, take d mu phi, and now let's say minus g phi squared. Okay, now pause the video. I want you to work out what are the dimensions of g. Once you've got the dimensions of g, unpause. Okay, did you do the exercise? Good. You should have found that g was length to the minus 2. Okay, let's pick another example. Now I want you to take the Lagrangian density to be 1/2 d mu phi, minus g. Let's make it phi to the 6. And I want you to work out the dimensions of 5 to the 6. Okay, so pause the video and unpause once you've done it. Okay, good. Have you done it? Well, you should have found that g was length squared. And let's just box these so that there's lots of G's appearing. So the G stays inside the box. G's in the box mean the same thing. So what you can see is, in fact, having minus G phi to the 6 or minus G phi squared will certainly not give you a CFT. In fact, if you were to take the Lagrangian density to be 1/2 d mu phi minus G phi to the n, you would find that minus G phi to the n, only n is equal to 4, gives a G that is dimensionless. So if you apply the condition to be scale invariant at the classical level, so what does that mean? So to be scale invariant at the classical level, the theory must have no dimensionful parameters. You find that of this infinite number of interactions that you could choose, the only interaction that works is when n is equal to 4. So this should give you a feeling that at the classical level, actually, it's really not very easy to get a scale invariant theory. And of course, at the quantum level, things get even harder. So for those who studied QFT, so I'm going to assume you've done a little QFT now. So at QFT level, if you remember, we usually define the theory with some sort of a scale at which we do all of our normalization. And there was an interesting quantity that we defined. It obeyed we obtained it from the Cullen-Samanzik equation. And this looked like our mass scale, I'm just going to call it lambda, times by the derivative of our coupling with respect to lambda. And this told us how the coupling runs with energy scale. So you might remember this, that the beta function tells us about running couplings, and all of the parameters in our theory actually run with scale. If you really want no scale invariance, then all of the beta functions have to be equal to 0. And this is the condition for scale invariance, and of course, that means also for a conformal field theory. So you can see that the classical condition to have a conformal field theory is that your theory only has dimensionless parameters, but that's not good enough at quantum level. At quantum level, we must require that all beta functions vanish. Actually, we studied this 5-4 theory. You might remember this from last year. So when we studied this 5-4 theory, so let me just put it down again. This 1/2 d mu phi minus G phi to the 4, this theory has a beta function which is positive. That was one of the results that we learned. It's got a positive beta function. So at quantum level, it's not a CFT. Okay, so if you've got a theory that has no dimensionful parameters, then classically it is indeed scale invariant. But when you go to quantum level, it could develop a non-zero beta function through the process of renormalization. And if it does, you don't have a CFT. Actually, it's incredibly difficult to come up with theories that have a vanishing beta function. It's not easy at all. And that tells you it's not easy to construct conformal field theories. So I was meant to be convincing you that conformal field theories are relevant for nature. And I keep giving you more and more evidence that it's hard to come up with a conformal field theory. Well, hang in there. We're going to keep going. And, well, let's just keep going.